Hello everyone, welcome to the first tutorial of MTE 241. In this tutorial we are going to cover the first and second problem sets that are already uploaded to the Learn. So let's jump to the questions. So the first question is about how can we address a main memory space. So basically, if a bus has 20 address bits, what is the maximum amount of main memory that can be accessed by such a bus? How about 32 address bits and 48 address bits? Answer using appropriate size prefix like KIB, megabyte, and gigabyte. So basically, we know that a memory is sized in power of 2. So if we want to address a 20 address bits processor, we can simply say that there are basically 20 address bits, and we can basically access to that space by 2 to the power of 20 bytes. So there are 2 to the power of 20 bytes space available by this size of address bits, which is equal to 1 MIB. So the same case will exist for 32 address bits, and it would be 2 to the power of 32 bytes for sure, and it would be basically 4 gigabytes. And if we have 48, the same thing, 2 to the power of 48 bytes, and it would be 256 TIB. I believe that this was simple enough to follow. Okay, let's go to the second question. In this question, we have this device, which is a 2 terabyte Seagate drive model, and it has 2 disks with data on both sides of each disk, which means that if there are 4 read-write heads, and it guarantees this amount of 512 byte sectors, but actually stores data in this amount of 096 byte sectors. The distance from the spindle to the outer edge of each disk is 1.25 inches, and the average track density is 352,000 tracks per inch. So the question is, what is the average number of sectors per track? So the first thing that we want to do is that we want to know how many tracks exist in total. So we know that there are 3, 5, 2,000 the unit is tracks per inch, and we know that the space is 1.25 inch per basically disk. And then since we have this number, and we know that there are 4 disks in total, as we can see here, so the number would be 156 zeros. So this is the number of total tracks which is available in this device model. Okay, and now we want to know that what is the average number of sectors per track. So if we know that we can basically these number of bytes are available to us, so what we can do is simply we say 488,378 646. This is the number of sectors that are available, right? Divided by 176,0000, which is the total number of tracks. So here we have 277.5 sectors per track. So this is the average number of sectors per track for this device model. Okay, so let's go to the next question. So the next question, which is question 3, basically, suppose that we have a 32-bit address processor with a virtual memory uses 4 kilobyte pages. The question is how many entries are in each processor's page table. So the first question is, what is the virtual memory? So basically, virtual memory is a process of mapping a logical address space numbered from 0 to the physical address space that we have or exists in the computer, so that the RAM serves as a cache for the program's memory stored on the disk. Basically, the virtual memory is used to increase the performance of the processor. So first of all, we want to know that what is the physical address space that can be basically used. So the physical address would be address space actually would be 2 to the power of 32, which so 2 to the power of 32 basically byte. So since we have 32-bit processor, the total page table, as we can see in the question, is 4 KIB. So 4 KIB means that 2 to the power of 12 byte. This is the the total page table. So the number of entries in each table, so the total number of page entry in this case would be 2 to the power of 32 divided by 2 to the power of 12, which is for each page, and then which is the total page number table, which will gives 2 to the power of 20. So this is the number of entries in each page table. Okay, so the next part of the question is asked, if each page table entry is 4 byte in size, how much memory is occupied by one page table? So basically from the previous part, we know that there are 2 to the power of 20, 2 to the power of 20 entries, and each entry according to this section is 4 byte, which is 2 to the power of 22. It gives us 2 to the power of 22 byte, which is 4 megabyte. So this is the total number of total memory occupied by one page table. The next part is asking, if there are 16 processors and main memory size is 4 GB, what fraction of the main memory is occupied by the page table? So in this case, we know that there are 16 processors, and each processor is 2 to the power of 22 byte. So the total occupied memory for 16 processors would be 2 to the power of 4, which is 16 processors, multiplied by 2 to the power of 22, which is what we get from here, right? So this gives us 2 to the power of 26 byte, right? So now we want to know that we know that the total main memory is 4 GB based on this section, based on the question basically. So here we know that there are 4 GB, and then if we want to know that what is the occupied fraction, it would be 2 to the power of 26 divided by 2 to the power of 32, which is the total memory size, which will gives us 1.56% of the total main memory. Okay, so let's go to the next question. So the next question is asking about write a C code that is as close as possible to the C++ piece of code that is provided in this question using a struct and some function. So first of all, we need to know that what is different between the C and C++ code in this piece of code. So basically, in the C code, we don't have any class. So first of all, this class needs to be converted. The second, the sum function cannot works like that, because we need to basically, the x and y will be, if we want to basically convert this class to the struct, we need to pass the struct type. So the second differences will be the sum function and how we pass the argument. The third one would be how we allocate the memory. So in this case, we have class, so we knew an object from this class. But in a C, we don't have any class, so we cannot new an object from a class. So we need to figure out how should we basically change this one. The fourth one is cout. We don't have any cout in C code. Instead, we have printf. So we need to basically figure out that one. And the last one would be this delete function, which basically, again, we don't have any delete function in C code. Instead, we have other function that is responsible to deallocate the space. So if you want to, first of all, we are going to change this class to a struct type. So the structure will be something like this. So if I'm going to use the type def, a struct, it's a normal way to defining a struct. I will call it A, and then there are two members, X and Y, and then I'm done. So this is how we convert this class to this structure. Then we want to basically change the function as well. So we have a sum function. We will keep the name as it was. And now we cannot pass X and Y because X and Y are members of the struct. So what I'm going to basically pass is an object of this struct, which is pointer to the A, and then I'm going to return whatever I would like to do, which in this case is AX plus AY, and then I'm done. So the third thing, which is this new, so I'm going to change it to this one. Instead of newing, I'm going to malloc to allocate some space with the size of A. And for this cout, I'm going to use a printf with its argument, and it's important to change this A, say sum, to sum A, because this A is malloced here, so it's fine. And then instead of using this delete, I'm going to free A, which is basically the same one, except that it is in the syntax of basically C code. Okay, so we are done with this question as well. So let's go to the question 5. So here we have, assume that we have a header file, day.h, that contains the following definitions and declarations. So let's look at the code. First of all, we have a structure called time_t, which includes an hour and a minute. And then we have another struct which called event_t, which include a name and a start, which the type is basically time_t, which is defined here. And then we have a duration, basically, which is the duration of the event in minutes. We have two functions that we need to develop here, and these are the output that we are looking for. So here in the output, it is clear that we want to sort them such a way that the event that start earlier will be printed first, and so on and so forth. Okay, so how can we basically develop these functions? So let's look at how the main looks like. So we have events consisting of the lunch, breakfast, and so on and so forth, with the time, start times, and also the duration. And then we will get this n, which is the number of events that exist in the file. And then we have the sort date that we need to basically develop, and the print function. So for the sort function, it's simple enough. The thing that we are going to do is simply we are concerned about an I. So let's say that we take an event, then we will compare with the event of the previous event that exists in the file. In this case, J. It's the previous one because it's I-1. And then if the start time of the I is basically less than the start time of the J, what we are going to do is that we will switch them together such that the event that starts earlier will be basically go first in the array that we have. Okay, and this function is simply, the compare function is simply gives us basically that compare the start times of two events, which is basically a straightforward function. Okay, so now we know that how it's sorted. It's simple enough. And then we are going to print it. So the only thing that we need to do is that since we are looking for, so if we look at the how the output should looks like here, it says that the breakfast from 7:30 a.m. to 8:15. So 8:15 is the end time, and we don't have end time in our file. It's just the start time and the duration. So what we are going to calculate here in the printf is that we want to find out basically what is the end time. Basically, it's a simple math such that we have the hour multiplied by 60, which will gives us the minutes plus the duration. So that will gives us basically the end time, and then we will going to print it in an hour in a correct manner with the hour and minutes and stuff like that. Okay, so let's go to the next question, which is question 6. So write a C program to determine if the processor is executing on if the processor is using a big endian or little endian. So what does it mean? Basically, it means that in what order the processor load and store the bytes of the multi-byte value. And basically it depends on if the processor is implemented as a big endian or little endian. So the big endian means that, so if we want to quickly give a description of that, so the big endian means that it load or store the MSB first. So MSB is a most significant bit, and the little endian means that it load or store the LSB first, which is the least significant bit. So let's look at an example to see how it works. Assume that we want to store 0xA1B2C3D4 to the address space of 0x20. If we are using a big endian, we are going to store the MSB first. So what we are going to do is that we will store A1, which is the MSB of this multi-byte data, to the 0x20. Then we will store B2 to the space of 0x21. Then we will have C3 to the space of 0x22, and then we will have 0x D4 to the space of 0x23. So this is how it looks like. And instead, if we are using the little endian, it means that we are going to store 0xD4, which is the LSB, to the space of 0x20. Then we will have 0x C3 to the space of to the address of 21. Then we have 0x B2 to the space of 022. Then as the last one, it would be 0x A1 to that is the space of 0x23. So that's it. That's how the little and big endian works. Okay, now let's go back to the question and answer how can we answer that question. Okay, so for this, so there are a couple of solutions for basically determining what the processor is doing in terms of the little endian or big endian. So first, one of those is using the union structure. So the union structure basically works such a way that all of its members will be stored in the same place, starting in the same place. So if we have, in this case, we will define a union, and then the x will be 16 bits, and the y would be 8 bits. Look at the uint 16 and uint 8. However, the y would be basically the arrays of 2. So what we are going to do is that we will store a multi-byte data to A. A multi-byte data in X. Here, for example, 0xAA55. And the only thing that we need to do is that we compare the Y0 here to the 55, which is the LSB of this multi-byte data. If it is equal, it means that it uses a little endian. On the other hand, if it was not 55 and it is basically AA, it means that the AA, which was MSB, is stored first. It means that basically it was big endian. So in this case, if the Y0 is equal to 0x55, it means that the 55, which is LSB, is stored first, and it means that it is little endian. Okay, I think that that's a straightforward calculation. But anyway, this is for the sake of the answering this question. But if you want to know if a specific processor is little endian or big endian, you can simply go to the like data sheet of that processor. It should be clearly stated that. But for the sake of programming, it is one of the ways that we can basically determine if the processor is using little endian or big endian. Okay, let's go to the next question, question 7. So it says, write a C program to determine whether struct padding is employed by the compiler or not. So what is struct padding? So in order to align the data in memory, one or more empty spaces or bytes or addresses are inserted or left empty between memory addresses which are allocated for other structure members while memory allocation. Basically, this concept is called structure padding. Now, the way that we can basically determine if there is struct padding or not is that we can define a struct here. So the first member of the struct is 8 bits, and the second one is 32. So what we can basically do here is that we can simply check if the address of a second element of this structure is immediately after the address of the previous member of the structure. So if in other words, if A and B are allocated spaces in a memory back to back immediately, it does mean that there is no struct padding. But if their spaces are basically separated by more than 0, so it means that basically there is some empty spaces or slacks between these two spaces. So what we can do here is that the only thing here, we would basically compare the address of A plus 1 to address of B. So in this case, we can simply see that if there is any space between them or not. If there is, it means that if the address of A plus 1 is the address of B, it means that there is no struct padding, there is no space, empty spaces. And if it is not, it means that struct padding is used by the compiler. Okay, let's go to question 8, which is a simple question, I believe. So assume that we have this piece of code. We want to see basically what would be the contents of the stack when this program is at the lineup labeled here, which is this point. So first of all, we will start with main. W is 1. F3 1 will be called. So we will go to the F1. Then what will happen is that we will go here. It returned 5. Oh, sorry. So we are not going to, it's not F3. So it's F3 1. So F3 is here. We are going to here. The B would be, in this case, f1, 1 and 1. So here f1 and 1 would be here. It returns I guess 5. So here b would be 5, and then we are going to f2b, which is f2 5. Then we go here, and the value would be 5, and then print the 5, and we are done at basically we are at the label here. So in general, we would have a as 1, b as 5, w which was 1, and the value which is 5. These are the basically values of the stack when we reach to the label here. Okay, let's go to the last question, which is question 9. So list variables names a, b, c, and d in a sorted order, sorted by the magnitude of the memory address they store. So as a general rule, we know that that variables will be stored in the memory in the order of first global variables, then we have the dynamic variables or heap, and then we have the local variables or stack. So basically, first of all, we need to look for the global variable. So in this case, a is pointing to the w, which in this case w is a global variable. So a will be basically stored first. So because it is pointing to basically to a global variable. Then we will have to look for the dynamically allocated data. So in this case, we have y, which is a malloc. It means that there is the dynamic assignment allocation of the memory. So c is pointing to that y. So then we have c. And the last ones, which are b and d, are pointing to the local variables. If you see, there are local variables. So they will be stored in a stack, but there is no differences between them. So either we could have b and then d, or we can say that we have a, c, and then d and b. So both of them are fine because there is no preferences or priority between them, and they are both going to store it in a stack depending on how the compiler decide between each of those. But both cases are possible. Okay, so that was the first tutorial that is basically covering the first and second problem sets. Since we are doing everything virtual, please feel free to ask any question that you might have in the Piazza or through email, wherever is basically you prefer. And I hope that you have a great virtual term at University of Waterloo in MTE 241. Thank you, everyone. Have a good day.